So we are going to learn conservation of energy after we have learned what is work and energy. So let's recall, we have learned that how to calculate the work from a force and displacement. For example, we have force this way, but the displacement, which is change of position from here to here, and if there is an angle between force and displacement, then we are going to calculate work as force times displacement times cosine theta, the angle between F and S. And then we have work energy theorem. So if you find out all the work done on the object, this net work would equal to the change of kinetic energy of the object. So basically that's what we learned for last chapter. Work, how to calculate the work, and then work energy theorem. We're going to learn work energy theorem in this chapter. Use work and energy theorem in this chapter too, so pay attention. Now today, in chapter 8, we need to clarify what is potential energy. What's the definition of potential energy? After we introduce potential energy, we introduce another very important concept, mechanical energy, and what kind of circumstance mechanical energy should be conserved. So it's not always conserved, but under certain condition it's conserved. And then we have conservation of energy. Now, conservation energy is a universal. So basically there is no condition for it. Energy is always conserved, and we're going to talk more on this later. Now this has condition, conservation of mechanical energy, condition. Now you need to pay attention during the lecture what would be the condition for mechanical energy conservation. Now first let's study a simple concept, power. Now if you pick up any electronic device, basically your cell phone, your computer, or the light bulb in your house, you will see something 20 watt, 5 watt, or if it's a refrigerator, it might be 1000 watt or 2000 watt. That means how many energy it consumed in a certain amount of time. So, and we call that unit of power. So power is how many work is being done, or you can see how many energy consumed in a certain time. Or you can say it's not work, it's change of energy over time. That's power. And the unit for power, as we discussed, is watts. And if we are using energy, time is 1 watt is 1 joule per second. Now let's do an example from chapter 7 we left. So Mactron, he used his weapon to shoot a Starscream with a very heavy mass Starscream, 10,000 kilograms. It's knocked back and slid a certain distance. Its initial velocity is 10 meters per second. How much work is done? How much work is done? This one. So okay, let me just draw a robot. Looks like Starscream, right? Okay, he is sliding back. Okay, so it's kind of, we also need to do free body diagram. You see, what would be the forces acting on Starscream when he is sliding back? You have gravity, and you have normal force, then you have friction. Now, that's normal force, there's gravity. That's displacement. That's friction. So you can say, what's the angle between normal force and the displacement? 90 degrees. And what's the angle between gravity and displacement? 90 degrees. What's so special about 90 degrees? Because 90 degrees is 0. So in this case, normal force and the gravity is not going to do any work. The only force that is doing work is friction. Okay, so now we need to recall work and energy theorem. The only force doing work is friction, and the kinetic energy of that theorem changed. And now we have work and energy theorem. Work done by friction should equal to the change of kinetic energy. And final kinetic energy is 0. Initial kinetic energy is 1/2 mass of that room, initial velocity of that room. You don't need to plug in all the numbers. M is 10,000, right? 10,000 kilogram. V is 10 meter. So you calculate if the energy done by friction is negative 500,000 joules. That's the work done by friction. Now, why the work done by friction is negative? Which is easy to understand because displacement is in one way, friction is in the other direction, so the angle between them is 180 degree. Cosine 180 degree give you negative. Okay. This is part A. Question B, I think it asks us what's the coefficient of friction. Coefficient of friction, well, we have the equation that friction equals mu mg, and we know this one. If we want to calculate what is mu, we definitely need to figure out what is friction. Now, we already know the work done by friction, very good. And by definition, work done by friction is friction force times this displacement, which is 25.5, right? So using this information, you can calculate friction is work done by friction over this displacement. That's the magnitude of friction. You'll find is, and then mu is F over mg. Mg is 100,000 kilogram times 9.8, right? You plug in with the number. I think I find mu is 0.2. What is the power? Power is change of energy over change of time. Change of energy is 500 joules. Change of time is 5 seconds. So power is 100,000 joules. Okay, that's an example from chapter 7. Now we start chapter 8. We have to introduce two different kinds of forces first. We have conservative force and non-conservative force, which has nothing to do with Republicans and Democrats. It's conservative. Now, in physics, conservative force is defined as this. Now, you imagine you have one object and move from position 1 to position B. Now, between position 1 and position B, there are numerous paths. You can take this path, path 1, or you can take this path, path 2, or you can even take any other path. For conservative force, it's very special. So the work done by the force from position A, position 1 to position B is independent of the path it took. So whatever path you took, the work done by the force is the same. So non-conservative force, the work done by this force is different if you took different paths. So now let's just put it on the table. Gravity is a conservative force. Basically, we're only going to learn two conservative forces in this semester. Gravity and elastic force, which means spring force. So let's think gravity. So you have a box here, you want to move it to here. Now you have a stair. Let's assume this object is very small. You can follow these stairs and go there. Then what will be the work done by gravity in this case? Gravity is always pointing down, mg, and your displacement here is pointing up. So gravity is doing work mg that h1. Now if you are going entirely horizontal, then your force and your displacement is 90 degrees, so there is no work done here. Only work done here, zero work done here. And then you are doing work here, zero work here, doing work here, zero work here. And you can cut h to different steps, h1, h2, h3. Now you sum them all together, you will find that in this case, you move object from bottom of the stair to the top of the stair is negative mgh. This is for one stair. You can have a different shape of stair like this. Just two steps. This is h. And if you do the same thing, you'll find this your h1, 0 work horizontally, h2, and add up, so the work done here is also mgh. Now you can even have this shape. You just move your object, and if you can cut this into very small stairs, very small, just like you do calculus, and this numerous of h, this is h1, h2, hn, you add them together, this h1 plus h2 plus hn should give you h. So the work is also negative mgh. You see. So I hope I convinced you that no matter what kind of stairs you build, as long as the total height is h, the work done by gravity is negative mgh. So which we kind of loosely prove that the work done by gravity doesn't depend on the path it took. It only depends on the initial position, final position. Actually, it only depends on the initial height, final height, right? For the work done by gravity. So that's one way to show that the gravity is a conservative force. The work done by gravity is independent of the path the object took. Okay, what is non-conservative force? Example, friction. If you have a box, you want to move it from position 1 to position 2, you can go straight, which is the shortest distance between 1 and 2. Or you can go around the room, going past 2. Now, from geometry, we definitely know that past 2 is longer than past 1. And what's the work done by friction is always Fs. And F is a constant throughout wherever you move it. So if you increase your displacement or the distance you moved, the work done by friction increased. So the work done by friction depends. Indeed depends. It does depends on which path the box took. And this is why friction is a non-conservative force. Okay, let's stop here at part 1 and then we'll continue our discussion in part 2.